Hello, good afternoon. This tutorial number 12 is under IEEE Symposium series on computational intelligence. Today, December 4th, 2022. The title of the tutorial, Machine Learning Models, Adversarial Attacks, and Defense Strategies. We have here three presenters, myself, Dr. Dipankar Dasgupta, followed by Dr. Kishore Dattagupta and Dr. Aruna Rai. We are part of the Center for Information Assurance at the University of Memphis. And I'd like to give the disclaimer that the views, opinions, and findings expressed in this tutorial are those of the tutorial instructors, and the information that are collected from the sources due credit to the original contributor who works on this referral here. So with that, I like to go to our speakers here. So you can see our pictures of the tutorial speakers and their affiliations. And now I'm moving to the agenda for the tutorial. I'll talk about AI ML algorithm and applications, and algorithmic bias and adversarial effects, principles of ethical and trustworthy AI. Followed by next presenter will talk about adversarial ML and its variants. Then talk about generative adversarial networks, followed by Dr. Kishore Dattagupta will talk about the adversarial supply chain and in deployed ML systems. Then he'll go also at length on defense strategies. Now, regarding the AI ML, there are more than 50 different algorithms which considered as AI algorithms or heuristic. Some are model-based, most are data-driven. And all these algorithms rely on data quantity, quality, and reliability. Learning models include supervised, unsupervised, semi-supervised, reinforcement, real-time, incremental, online, so on. There are many variations of these learning algorithms nowadays. The thing is, all models require parameter tuning for efficiently use as decision support to perform detection, recognition, classification, prediction tasks, etc. So one of the important things, there is no magic here. So it required significant amount of knowledge of the parameters, how they behave, and that parameter tuning varies from application to application. So using AI ML as a black box may not work efficiently as the environment changes. So as I move forward with this, then the performance typically varies with training and focus on generalization and specialization. If I like to make a AI model more general, it can cover more solution space, but may not be sufficient to give precise solution. At the same time, if we train any ML AI algorithm for significant amount of time, we call it overfitting, then it becomes specialized algorithm. So another thing is very important for newcomers to the field. You can see here, there are a wide variety of algorithms, including neural network, naive Bayesian algorithm, regression, evolutionary computation, machine learning. But if we look at the what falls under, so AI is not equal ML. That's to be clear up front. So as a superset, algorithms cover everything. Then under that, AI is one type of algorithm. ML is a type of AI. And then artificial neural network is a type of ML, and then deep neural network is another under artificial neural network, and like CNN and BeliefNet and all other neural network. So in old days, there were division between symbolic AI and non-symbolic AI. Non-symbolic AI, primarily the machine learning neural network, all this. Symbolic AIs are which use the grammar rules and different kinds of decision support system to build the expert system that those are in the old days. Also, AI applications, you can use a single AI method, which we call it a narrow AI, or a combination of algorithms which can make it general AI. To make it more robust, it is essential to know that general AI, and nowadays there are a company called OpenAI, those are the way to go to have a bigger solution. Now, there is also a new area called generative AI, where you can create objects from existing or new synthetic objects from text, images, and videos. That's an interesting area, need a lot of scrutiny, and its advantages and disadvantages before we can move forward with these technologies. And again, I'll talk about how important is this AI standard or ethical use of AI become essential as we come forward. I'm going to start with very simple concepts of machine learning, where you can see that you give the input. Here I'm showing the data-driven model. You're giving the input, and the machine learning model, you then collect the features. That's called feature extraction. There are many different feature extraction algorithms out there, clustering, then data fusion methods, and then it feeds to the different machine learning algorithm. Sometimes they call classifiers, other times they call it predictor, which will give the output. Output in many times is a probabilistic output. Here again, if the outputs are deterministic, then you don't need a machine learning algorithm, but the output need to be quantified for any decision making. There is another example where deep neural network, where different kinds of neural networks are used. Again, the input and followed by this neural network model. There are several neural network models exist. The simple one is multi-layer perceptron, recurrent neural network, Hebbian learning. Now on the deep neural network, you have different sectors, and I'm going to show you next. Then that requires some training. Some are supervised, some are unsupervised, some are reinforcement learning. And here in this case, we are showing that that the data is fed, and you have a training process which will differentiate, classify, and put in different categories. That training process will do that, and the model is trained, and whatever that model is. So ML model is trained, and then this shows the interface when you apply, and there are many existing tools there. You give the input, the testing phase, and it will produce the output. It will produce the output depend on how good the model is trained here. So, and that is in the good situation. You expect, you train well the system, and the system will produce in the inference, as an inference when you do the production or delivery end. So, and more complex neural networks are coming, and they are called convolution neural network, Bayesian neural network, belief network. So here, the idea is the input is a much more complex pattern. Many times these are images, but image is not the video, audio, all can be used, because that signal is converted into the digital input, and then go through different convolution layer, encoding layer, and it goes through different transfer functions. There is intermediate processing, where max pooling layer does the information truncation and followed by another set of convolution layer. And again, how many of those depends on the application, and there is a fully connected neural network that give the end decision. So if you put a car, it should give you a car, and if you put, so if they trained with different kinds of inputs, it should be able to as expected. Now, nowadays, all machine learning techniques or any intelligent systems are not standalone. They are cyber-enabled. They are connected to operate remotely. They put them across geographical regions. So AI/ML moved from pure research to applications and products in last 50, 60 years, starting from standalone expert intelligent recommendation systems to mobile AI agents, bots, to global ecosystems. So AI/ML approaches are being used for fun, entertainment, business, government, society, and beyond. But the line is becoming blurry between real and fake for human to understand. And I'll give you some examples what I mean by that. So do AI/ML needed or useful for all applications? That's the question all we have to ask before using this technique. Probably not, according to me. Where the search space, the problem that you are trying to solve is relatively small and linear trajectory, that means reaching to the goal or learning is not difficult in any classical methods, and it's not multimodal or discontinuous or multidimensional, where you need this kind of complex AI/ML algorithm. Many algorithms nowadays labeled as AI/ML are not really AI/ML. Support vector machine, the regression analysis, they are beautiful statistical methods, but they are now labeled as AI/ML. It can be data science, but not AI/ML, according to my analysis. I have been in this field for last 35 years, and I have been seeing all these methods and worked, written books about those. So that's my conclusion, that all AI/ML now you will see in practice are really not AI/ML systems. Sensor IoTs are being used for data collection, processed using AI/ML techniques for real-world decisions and actions. So that's resulted in an autonomous system. So AI-based autonomous system becoming more useful in many real-world applications, drone operations, and autonomous vehicle, and many others. Most AI/ML-based systems of today and future will be cyber-enabled, putting this an additional risk of getting compromised, manipulated, destroyed remotely much more easily than we would like. So cyber is risky. There are a lot of cybersecurity issues. Now, when you put AI/ML to operate on that cyber-enabled situation, then the security and privacy issue become an additional burden because of the cyber technologies are relatively vulnerable to attacks, disruption, breaches. So that's the situation today, that the cyber-enabled AI/ML systems are become a norm and in wide use. Now, as we know that AI applications, because of its potential benefits, are now being used all across, starting from the finance, gaming, astronomy, healthcare, transportation, agricultural, education, e-commerce, entertainment, robotics, automotive, social media, data security. So you can see so many applications, and yet more applications coming. So AI-based technology is rapidly changing impacting our business, health, work, society, and government. So we need to think about the AML system. What are we going in the right direction? If the right direction can be well managed, trustworthy. That's the topic of the day. And because of this application, I'll show one or two applications. Those are very interesting, but I'll also say where there are risks. So here is the growing use of AI/ML. You can in AML applications is growing to 35.8 billion in a year. That was from 2 years back, but that number is significantly increasing as the business in retail, banking, service sector, smart and intelligent healthcare system fraud, as we listed in previous slide, that is tech giants like Google, Facebook are opening new AI/ML-oriented office and centers with skilled employees. Other small and mid-sized companies are creating new marketplace for AI/ML. And again, the US government is also investing $2 billion over the next 5 years towards new program advancing AI at artificial intelligence. Such trends with momentum finances are expected to grow the application of AI/ML in a significant way. Here are some examples. Now you can order customized dresses based on your body shape and structure or the type of things. So the customized dresses can be produced and delivered. So that's the industry, and this is one of the many examples that people can buy customized clothes online. Then here is another situation on doing that is if we don't use the AI algorithms in proper way. For example, online search software agents which suggest a fewer possible options or take biased decisions on behalf of the human and directing its activity towards achieving goal which may not be fair or competitive. This gentleman is trying to look for variety of dresses to order from. If the search algorithm doesn't show all possible dresses that they can choose from, for example, this is not shown, then it is showing the suboptimal solution and which become non-competitive from there, and the customer is in disadvantage. So basically software agents recommending a product or service without searching all possible options, or even if it is that is not showing to the customer. Here is another situation that people negotiate and make deal through physical world, and negotiations happen, and there is a contractual agreement, and everything happens in physical world. But assume that there is a collaborative agents who are making decisions and fixing prices or establishing trade terms not in a proper way, and that can cause serious effect on the receiver side. So in this example, that if the price fixing happens between agents where no humans are involved, then who will be responsible in those kind of situations? That is a point which will be coming, and addressing those are becoming very important. So here is another situation. Recent report says that that there is a flawed AI makes robot racist or sexist, and you can see New York led by several universities, including Johns Hopkins, shows that neural network built bias internet data teach robots to enact toxic stereotypes. So again, that's another area we'll be talking about. And lastly, the game that is we are coming in, that the fiction to reality, that the role of AI/ML, that AI/ML can take multiple roles or sometimes can take dual roles. So in case of image, audio, video, that's a very, very interesting. Some of the fiction now become reality to the people who doesn't understand. As we know, a picture speaks 1,000 words, but as it turns out, it is not the case on the cyber. Anyone with a smartphone can now make deepfake. We are not ready for what happens next. Fake porn videos are being weaponized to harass and humiliate women. Everybody is a potential target. And more interestingly, AI-powered art and animation tools, Umbo, Night Cafe, Terraria, and Midjourney, Dell-E, etc., produce realistic images and videos that can cause a range of harms, such as reinforcing racial and gender stereotypes or plagiarizing artists whose work was siphoned without their consent. Fake photos could be used to enable bullying and harassment or create disinformation that looks real. So there is a comment from one of the computer scientists that once the line between truth and fake is eroded, everything becomes fake. We will not be able to believe anything. And that's where the danger of these tools coming, where as long as these are fun and entertaining, that's okay. But if it crosses the border, use it for advertising, making people stereotype, that's where the problem will be. So now, with looking at all these things, I extended the adversarial machine learning definition with this following points. Adversarial AI/ML should not only consider attack and manipulation of inputs and or models, but also algorithmic discrimination of and bias, which mislead decisions and cause harm to people. So the extended definition for adversarial ML, AI/ML, should include algorithmic discrimination. And if we go further explanation on what is algorithmic discrimination, algorithmic discrimination occurs when automated systems contribute to unjust different treatment or impacts disfavoring people based on their race, color, ethnicity, or other classifications protected by law. Then automated AI-based tools for digital media, whether it's audio, video, or image, manipulation to mislead people, privacy, not well evaluated, and may result in misleading customers for unreasonable profit. So this all constitutes the adversarial machine learning use. Now, the first thing is the bias, and we are going to talk more about the bias now. So you can see the bias is has many folds and facets. The bias can come from data, and we call it data bias. Bias in data can exist in many shapes and forms, some of which can lead to unfairness in different downstream learning tasks. For example, historical data, unbalanced, the way data is collected and sampled, processed, and presented, measurement and evaluation, the way we choose, aggregate, and utilize and measure a particular feature during the model evaluation, then behavioral and observational data we collect through the web. So all this can create some form of data biasness, and I'm going to show you next an example how the self bias created in repeated loop. So now that's for the data biasness, but less spoken term is the algorithmic bias. When the bias is not present in the input data, but added by the algorithm. For example, framing the problem. How you formulate the problem to solve, there can be a bias embedded. Collecting and preparing the data, that the pre-processing and during the training, and interpretations of data and decision manipulation, where once the output is produced, how you interpret and in the decision making. So we need verification method that can help to detect and mitigate hidden biases within training data, and that mitigate the biases learned by the model regardless of the data quality, and provide explanation for decisions. We'll talk about explanation later, but let's see the situation here. Here, in this scenario, you can see example of biased data and use Stain's algorithm behind the web-based application delivering equally biased result. So here, this web portal is collecting data about human activities, whether it's a exercise, whether it is purchasing pattern, whether it is interest in different areas. So the data collections is happen, and again, it is hard to get a complete collection. It is always incomplete. Even if it is incomplete, data is generally huge. So activity bias, collection, sampling, and then from there you take the data that is collected for algorithms processing. So when you do that, there is a sampling bias. What kind of data you collect? How often you will collect? So if the data is continuous, you have to sample it after few intervals within a second, and that can miss some of the valuable information. So sampling bias cause that, and then algorithm, the way is written based on the formulation of the problem, that also have a algorithmic bias if they're not selected correctly. So, and that bias, the algorithm or the model that will produce, it will be through some interactive screen that will be displayed on the graphical user interface on any interface. And then human will select what to take, what not to take. When there is human involved, there may be a self-selection bias exists. And then, again, that feedback is given to the web as an output, that what the human feels as to the rest of the world. That selection also have a bias. So that is a second order bias. So, and they can also feed to the algorithm for further improvement. So first bias, second order bias always exists. So bias created through our interaction with websites and how and use recycling back to the web or to the web-based system, creating various types of second order bias. This is a very interesting article published in Communication of the ACM in 2018. Very relevant here. Then next, you see the many examples of biasness, right? Study found the Amazon's internal hiring tool that penalizes female candidates. Commercial face recognition, analysis recognition platform that are much less accurate for darker skinned women than lighter skinned men. And these are all reported. Facebook ad recommendation algorithm that likely perpetuate employment and housing discrimination regardless of the advertiser-specified target audience. So again, Gartner predicts that through 2022, 85% of AI projects will deliver erroneous outputs due to bias in data algorithms or the team responsible for managing them. So bias here is an example that police testing Amazon's face recognition tool, Cognition, but it shows that it sometimes take wrong decision and that's disputed. So if we put everything together, this is how the biasness situation is. As you can see, the many reasons for AI ML bias in different domains. Now, look at this is the cycle. We have the world. From the world, we collect the data, we design algorithm and develop it, then we use it in the world. So it is a cycle, and in each of the areas, we have some issues. Like in the way we perceive the world, so real world patterns of health discrimination can happen. So like unequal access and resource allocation to the in the world view. This relates to the healthcare and discriminatory healthcare processes, who will get the service, who will not, and then the bias clinical decision making. So that's the area in healthcare in this example, the data collected from the world, and look at the data connection aspects. So discriminatory data collection, where you can see the sampling bias and lack of representative data sets. Pattern of bias and discrimination backed into data distributions. So sometimes it is difficult to collect data from different segments of the population, and that also create discrimination in decision making. Then it comes to the biased AI design and deployment practice. So power imbalance in agenda setting and problem formulation, who is developing the algorithm, and then bias and exponentially design, model building and testing practices. So that's the design and development part. Bias deployment and explanation and system monitoring, that's after the delivery. So these are in case of healthcare examples, and you can see application in justices that can also occur disregarding and depending on digital evidence, right, in the justice system, excavating global health inequality and rich-poor treatment gap, and then hazardous discriminatory repurposing biased AI. So in the decision making also, that's the use part has also issues in AI ML use. Let's move on to the so how to identify and managing bias. That's very critical. It is assumed that the bias is neither new or unique to AI, nor can bias be eliminated entirely. Rather, bias which are harmful must be identified and, to the extent possible, understand, measured, managed, and reduced. So that's the important thing, that how to manage, how to understand so that you can manage. So further, perception of bias are human judgments. Thus, perceptions of bias are intimately related to interpretation of the model output. So here in this diagram, in the NIST report, that we have to think about the managing the AI bias at the pre-design space. Then it needs to be translated to the design and development and followed by the deployment. And there are many people need to be involved at different stages. Stakeholder groups who are involved, who will get affected, they need to be involved. And the risk management group who will test, validate, and the standard development or the evaluation group. So they will work in concert to remove or not remove, to manage the bias in any algorithmic approach. So you can see engineers often assume the machine learning algorithms are inherently fair because the same procedure applies regardless of user. But technology is not neutral. It is how it has been implemented. This perception has eroded recently as awareness of bias algorithms and biased data sets has increased. Arguably, the absence of harmful bias is a necessary condition for fairness. With that, NIST came up with 37 different types of biases that may exist in human decision and developing AI algorithms of different types. So this report is very interesting to go over to understand different types of biasness and how we can build that AI ML systems which can be removed those biasnesses. So to remove biasness, one of the important things is designing ethical AI. So determining responsibilities for ethical AI is more complicated. There should be multiple responsible parties, and whoever developing the algorithm, designing it, code developer, testers, cyber, when it connects to the cyber, so cyber-enabled AI products, and the people who will be selling to the end user. So all these people have to be responsible in some ways in their role to have the ethical AI application established. So transparency and disclosure at every level be essential for establishing ethical AI. So explainability is related to transparency. If you want to do transparency, explainability. So when you get the explainability aspect, then it cannot be used as a black box. The white box model is typically considered explainable, whereas the black box model is not. So in other words, you cannot use AIML method just giving input, getting the output. You have to understand the inside algorithm. So, however, transparency does not guarantee explainability because it requires human understanding, users understanding, technology developers understanding how things are working. So that's the understanding of machine learning technical principles need to be clear. So NIST provided 4 principles for building explainable AI. So, and what are those principles? Explanation. By very truth, you need to have explanation why certain things happen. A system delivers, contains accompanying evidence, reasons for outputs and processes. So that need to be. And then meaningful is it provides explanation that are understandable to the intended consumer. So in other words, if I'm using AI for just X-ray diagnosis or disease diagnosis, the explanation should be meaningful to that intended audience. And third point is the explanation accuracy. How accurate that explanation is in that context. So is it the output or effectively reflect the system's process? The system may be doing one thing, I'm explaining a different way. That's not the explainable AI principle. So then knowledge limit. A system only operates under conditions for which it was designed. And when it reaches sufficient confidence in its, what is the knowledge parameter that it is embedded? what it can or what it cannot do. That limitation need to be explained. Further details on explanation on each of the terms, like delivers and contain accompanying evidence or reason for output or processes. Meaningful means system provide explanations that are understandable to intended customers. And we already gone through this. Again, explanation accuracy, knowledge limit, that we already covered here. Now, important thing is NIST characterize explanation by two properties: the purpose. What's the purpose of using this tool or technique? And the style. The purpose is the reason why a person requests an explanation, or what question the explanation intend to answer. Style describe how you present the explanation. So, and that presentation, how you present the explanation, it can be in many forms, and that form is shown here. So the explainability details, it can be, in a sparse way, or it can be intensive as you provide the details. So in other words, it can be one way, the declarative and explanation. So it is fixed and inbuilt, and it can also be some interactions, but continuous interaction on question answer. That's a better way of providing explanation details. And those can be provided in different formats: graphical or visual, or verbal, written, auditory, sometimes voice answer, or well, auditory alerts, or giving some siren, blood level, pressure level is high, giving sign. So that explanation can be divided into broad categories according to the NIST report, that self-interpretable, that the model itself can be interpreted by human being, or it can be post hoc explanation, where some additional tools, techniques, or human can be used for giving the further explanation. So post explanation seems to be in some use, and in that case, that post explanation can give a local explanation or global explanation. A local explanation can explain a set of decisions, or is a per decision explanation. In a global explanation, it will give the overall explanation of the model. So as we are seeing, even in explanatory details, there can be declarative explanation, just inbuilt in, and there may be a one-way explanation where there is some feedback, but that feedback may not be immediately available, but there is a corrective way of giving feedback. And you can see this is a sparse way of explaining, and to a more intensive way of explaining in a interactive environment. And the way the explanation can be provided, it can be graphical, visual, or voice activated, textual, many different ways it can be explained. And it can be a self-explanatory or interpretable, or it can be post ad hoc explanation. And the next illustration will give what the post and difference between interoperability and explainability in further details. Here, an interpretable model or interpretable model should provide user with a description of what stimulus, such as data point or model output, means in context. In doing so, it enables that the human to achieve insight by cueing value, goal, principles, in turn enable high-level decision-making. An explanation, so interpretable is human understanding of what it has done. An explanation of a model results in a description of how the model output came to be. Explanation thus seeks description of the process or rules that were implemented to achieve the outcome independent of the context. Here we need more technical people to convince that this approach is a right approach. So disentangling explainability, whether one can describe the mechanistic description of how a system made a specific prediction from interpretability, where whether a man can derive meaning from system's output for a specific use case, that these are the major differences between interpretability and explainability. Here is an example which shows how these things tie together. So machine learning model and human cognition, interpretable ML is concerned with the helping human generate interpretations of data and model output. So this is a typical machine learning model where you give the training data and family of models in there. This training data will produce an output, and then you or train the model. Then you use the evaluation data, that is the testing data or field data, and using that what it created, it will produce the output. So this model is created from this training. Output now will be produced as the test or evaluation data feed in. So that producing some results, model predictor, then how do you interpret it? So you can interpret with a technical experts, that is just give explanation of the presentation, what it means, right, in a more technical way, or you can use human cognition with some background knowledge to show the environment on which it is being produced. Maybe a scenario or setting sun situation, or a cloudy, bushy area, something with the background knowledge to give more interpretability to the. So, or it can be in a chart where pure results are reported in some kind of graphical answer. So, and that's the difference that in decision making, both in interpretability algorithms are those that contextualize data by placing it in the context of a structured background knowledge, representing it in a simple manner that captures essential, insightful distinctions, and then justify the corresponding output relative to the value elicited from human user. So here what I'm saying, the machine learning model produce an output, and then the rest of the part is the explanation and interpretability, more interpretable to the intended audience. It is better deliverable to the or benefit to the end customers. So next I'm saying that bridging the gap between ethical principles, we have seen the ethical AI require explainability and interpretability, and the practice through critical areas. So it found that that accountability, translatability gap, and implementation gap, if these things can be governed by some policies and procedure, we can have a better ethical AI models. So distributed responsibility and accountability on the accountability, so that will reduce the gap. Then transparency and documentation, having documentation, how things are, and then explaining it while implementation. And if these things can be governed by some regulation, by some governing body, and assign responsibilities to different groups, that gap between this misunderstanding or lack of understanding between the AI models or AI-based systems and human benefit, that can be reduced and can avoid any damage or cause harm to humanity. So Salesforce trusted AI principles, they highlighted it's on the same value that accountability and accessibility and transferability, that from principles to practice, how that can be done in engineering environment. So responsible, so work with human rights experts, educate and empower customers and partners, open development and share research. So that's the part of the responsible. So to build a responsible AI, so need to involve this type of people, human rights group, to make sure it doesn't affect any human being, and like others. Accountability, invite customer feedback, engage ethical use of advisory council, and external ethics review of high-risk AI papers, research papers. So that's the part of accountability, that somebody from the third party need to review, get feedback, and all kinds. And transparent means part of the explainability. Customers control their data and models, clear disclosure of terms, and that's we provide the transparency. Empowering, that again, educating is one of the important. Deliver AI research breakthrough, so that's the empire and inclusiveness. Test models with diverse data sets, conduct consequences screening workshops, and build inclusive teams. So this kind of giving a guideline to build trusted AI principles in production services, and based from the principles to practice. So following the responsible groups, how to do accountability, be transparent and empowering and inclusive to people. That's the recommendation from the Salesforce. Now, putting things together, MITRE proposed 7 connected elements for trustworthy AI. So to build all this explainability, removing biasness, providing interoperability, you need to reach to a system or product which is trustworthy. In this case, trustworthy AI. According to the MITRE Corporation, that transparent, again, same as before, it is clear how the data being collected, when AI being used, and how the decisions were being made. Traceable, are they able to trace the AI code and result? Then safe and secure, you can see responsible accountability as before, fair and equitable, explainable, and reliable and robust. So these are kind of similar things in more unified way that covers the 7 principles that to build the trustworthy system. Some of these reliable and robust involve security and privacy aspects of the model. Others are involve human accountability on all aspects. So withstanding the adversarial ML is a set of mandatory conditions for secure and resilient AI-based systems, and that's by NIST. Again, according to them, the NIST is developing framework to better manage risk to individual, organization, society associated with artificial intelligence. The NIST risk management framework, that framework is still under development, and that is intended for voluntary use. The ability to incorporate trustworthiness consideration into the design, development, use, evaluation of AI production services. Now, these are good guidelines, these are good framework, but the companies who are developing it need to follow those guidelines to make it more useful and more beneficial to the customers and the society. So moving forward, some regulations are coming. In April 2019, US lawmaker introduced bill called Algorithmic Accountability Act to protect from bias algorithms, deepfake, and other bad AIs. So you can see Federal Trade Commission created rules to requiring entities that use, store, share personal information to conduct automated decision system, impact assessments, data protection, impact assessment for evaluation, high sensitive automated system. So things are coming, but it need to be, those regulations need to be placed before large scale deployment in every area. So companies would have to assess whether the algorithm powering those tools are biased, discriminatory, as well as whether they pose a privacy and security risk to the consumers. Europe's top European officials on the digital economy said to companies such as AI, people need to be informed when they are in contact with an algorithm and not another human being. Any decision by an algorithm must be verifiable and explained. And that's the European Union crafted 7 principles of guiding AI development. So there are some guidelines and regulations are coming. So these are the references for this part of the talk, but I'm now moving to more on adversarial attack on the model on a technical sense. Now we know that AI can take many roles. Either AI can be used as an offensive system, or we call it offensive AI, or it can be a defensive. In case of offensive, AI-based tools are used for interruption of services, taking control over any decision, breaches, data breaches using AI-based techniques, cyber attacks, malware creations, hacking, misinformation. These are all offensive AIs. Now, in case of defensive AI are providing defense in depth, proactive, reactive patches, authentication, access control testing, surveillance. So you can see that AI/ML can take multiple roles, and under different role, it can take many facets of its applications. So security of AI need trustworthy AI to prevent data manipulation and Trojan AI. So that means model compromise. Now, adversarial AI in traditional sense, the manipulation of training data, machine learning model architecture, or manipulation of test data in a way that will result in wrong output from ML. So you can see this is a stop sign with some added noise. The system will show incorrect that green light. So car will go, cause crash and damage. Here again, in case of image, that Toby cat with 88% certainty with some random noise, the system will tell that it's a guacamole. So guacamole, so that's called the direct attack or adversarial attack. These are part of the algorithmic manipulation, and it can happen also in an audio case with some noise in a door alarm. How are you can produce open the door. Here you can see that if the model, in case here we have shown the neural network, model is manipulated, so input is 7. In a good case, it will show 7 if properly trained. But if the model is tempered, 7 will produce output 8. So classification or labeling got tempered, and here the model has merged, and in this case, backdoor classifier changed some of the weight space that also produced 8. So you can see data input can be manipulated and following. So next part of the talk will be by Dr. Arun Roy, and he's going to talk about this adversarial generative adversarial network, which can use for positive purpose and also for adversarial purpose. That's the part now you will listen in few minutes. With that, my part is over. Thank you again.
Hello everyone, this is Dr. Arnab Roy from the University of Memphis. I'm a research assistant professor in the Department of Computer Science. So today my topic of discussion is the adversarial machine learning and the generative adversarial network. I assume that all of us have the basic understanding of the machine learning. Hence, let us start our discussion with a couple of examples where we mostly find the applications of the machine learning. Now let us talk about the applications of the machine learning. So one of the applications is certainly the computer vision. So the area of computer vision has generally three classes of problems. One is called the image classification, the next one is called the object detection, and the last one is called the image segmentation. So now let us talk briefly on each of them. Now, to start with the image classification, if we try to classify an entire image as a member of one of the classes, we call it the image classification. For example, in this image, for example, uh, eh, eh, in this image, my question was, is this a cat? Then the classification module answers that yes, this is a cat. The next one is the image classification plus localization. That means which part of this image is cat, or which part of this image has a cat. So the classification plus localization module answers with a red box. That means within this red box you will have a cat. The cat is within the red box. Now the next one is the object identification. So object identification applies when there are multiple members involved in an image and we may try to identify each of the members present in the image. So for example, if we see this image, so it is a pretty common image. This has a couple of parties involved. So one is, one of them is a dog, two are cats, and one is a duck. So we encircled all the individual objects with one rectangles. So the red rectangles contain two cats, one blue rectangle, this one, contains one dog, and the green rectangle contains one duck. So we call this thing as the object detection. Now we can go even one step deeper. That means we can try to classify each of the pixels. For example, now in this picture we can see all the pixels inside this blue boundary. Inside this blue boundary are dog, are the pixels of the dog. Then within the red boundaries, these are the cats, and the green boundaries, this is the duck. Now this is called the image segmentation. Now in all the three problems, means the image classification, the object detection, and the image segmentation, we can find that the machine learning algorithm can perform better than the average humans. There are plenty of research works published which we can see in the internet. The second very famous application of AI and machine learning is the games. Now, a plenty of games use AI and machine learning, and some of them can be played well by the machine learning algorithms. For example, chess. Chess is a very good example of that. Then the snake games. Even we can quickly build a Python module for playing the snake games. Apart from that, there is AlphaGo, and many other applications can be found over the internet. Now, it is true that in many cases, we can unequivocally say that machine learning can play much better than the best human players available. The other application of the machine learning is the generation of the non-existent data. Now, this is another eminent application of the machine learning. Now, by the term non-existent data, we mean that the data generated by any computer simulation. And these data can be used for privacy protection, privacy breaching, increasing the size of the dataset, and even many more. Now, technically, we don't need the synthetic data, but sometimes it offers a cheaper and more time efficient solution, since the extra data may be a lot more expensive. Maybe it's time consuming. That means you need a huge amount of time to get it, uh, which doesn't make any sense. for the type of projects that you are working on. Now, let us see some of the examples of the fake data. Now, this is the fake. This is a yeah, this is a face, and this is another face. So both these two faces are fake. Both these two faces are fake, and they are mostly generated by the StyleGAN2 application. Now, it is impossible. It is highly impossible by any human to identify them as fake. Now let us see the gradual improvement of the image quality generated by the machine learning models. These are mainly some GAN class of models that we will discuss later. Now this is generated in 2014, which looks quite blurred, but still a real looking face. I can identify this as a human. Now this is generated in 2015. Now it is much better than that of the 2014. Now 2016 is even better. 2017 is even better than the 2016, and the 2019 is very good, very convincing. None of the humans can say them as fake. Now, as we already mentioned, that these are generated by the models called the generative models, or especially the generative adversarial network, that we will discuss later in this talk. Now, the other applications of machine learning includes one, fingerprint recognition. The other one is the speech recognition in car, cell phone, etc. So spam filter in the email. So it is a pretty old application, and almost all the email applications include spam filter detection. So they're the next word prediction and many more. Now, these are all the applications of the machine learning. But one thing we need to say that, we need to think one thing, that is that behind all these examples, the model developers had to solve some standard mathematical problems. So, for example, let us focus on the image classification problem. In the image classification problem, our goal is to get an F, the function, which maps an image to its content or the category or the class, whatever you call. We know the value of f on the label data, and the goal is to get an accurate approximation of f. For example, see the human face below. So the goal of the accurate approximation of f is to map this human face to the label human. More generally, it could be a supervised problem. In the supervised problem, we try to approximate this f using a finite label dataset, which often we call the training data. See the training data here. This training data decomprises of xi and yi. So here xi's are the images and yi's are the corresponding labels. Now, as we discussed earlier, that the value of f unknown in this finite data, that is the training data. So here the value of function f for xi's for a particular image is yi. This is a classical example of function approximation problem. So let us focus on the problem of generating fake human faces. So this problem is the approximating and sampling an unknown probability distribution. What we use here, so we use the random variable of the human faces, where we don't know the underlying distribution of this random variable. So we have a finite sample of the pictures of the real human faces. Then we approximate the unknown probability distribution and produce new samples of the fake human faces. So this could be an unsupervised learning problem where the machine learning algorithms are not given any labels, and these algorithms have to discover the hidden patterns in the data without the need of human intervention. So mostly this is a probability distribution approximation kind of problem. So in the previous slides, we found that in case of the supervised and unsupervised problems, we are mainly solving the classical function approximation problem and the probability distribution approximation problem. Next, we focus on the Go games, so where the system solves the Bellman equation in dynamic programming. So this is another classical mathematical problem. In short, the moral of the story: we are generally solving some classical problems like 1. Function approximation, 2. Approximating the probability distribution, and 3. Solving the differential equations like ODEs and PDEs. Now, we need to understand that these are classical mathematical problems that mathematicians are solving for a very long period of time. Then surely the question arises, why machine learning? where there are plenty of sophisticated techniques available to solve all these problems. Now, the obvious answer to this question is dimensionality. Now, let us try to understand the dimensionality problem with the help of a data. Here we take the CIFAR-10 data. This CIFAR-10 data has 10 different classes such as car, plane, birds, horse, dogs, etc. mentioned above the columns. Now here the image size is 32 cross 32 with 3 channels, which gives rise to the dimension of 32 cross 32 cross 3, that is overall 3072, which is very huge. Now the interesting part here is that to classify this data, it becomes a function approximation problem in a 3072 dimensional space. That's quite huge. So let us talk about the dimensionality problems involved in the classical algorithms. So for that, here we approximate our function, that is f, using the piecewise linear function over a mesh size of h. Now we assume that d is the dimensionality of the problem. M is the total number of free parameters involved in the model. Hence, we can derive a relation among this h, d, and m in case of the piecewise linear function as follows. That is, h is approximated as m to the power 1 divided by t with a negative sign. Let fm be the approximation of f using the piecewise linear function. Then the error can be evaluated, that is, I'm talking about the approximation error, can be evaluated as in the next equation, that is mod of f minus fm. This is the approximation error. So we can see that it involves a quantity called t, that is the dimensionality of the problem, right? That means the approximation error includes dimensionality. Now to make it more clear, if we want to reduce the error by a factor of 10, then we need to increase m by 10 to the power d by 2, and we can recall that m is the model parameter, so our model becomes huge. Now for example, let us take the example of the CIFAR-10 data where d was 3072. We can recall it. So m needs to be increased to 10 to the power 3072 divided by d, that is 10 to the power 1536 by the same logic, and this quantity is so big that it is even unmanageable by any of the available classical algorithms such as wavelets, polynomials, piecewise linear functions, etc. Now these we call the cause of dimensionality, and apparently all the classical algorithms like function approximation using wavelets, polynomials like piecewise polynomials, trigonometric polynomials, etc. all are having this curse of dimensionality problem. Now even as d grows exponentially large, the computational cost of these classical algorithms becomes extremely huge. So in the last slide, we saw that almost all the classical algorithms are suffering from the curse of dimensionality problem. Now, the curse of dimensionality means the error terms involves dimension, and if we want to reduce the error, then we have to increase the number of free model parameters. That means the size of the model will be extremely large. Now, so this certainly implies that to efficiently solve all the mathematical problems that we discussed earlier. Now those mathematical problems include the function approximation, the distribution approximation, etc. Then we need to try with other solution techniques. And one such solution technique could be the deep neural networks. So in this slide, we try to understand how this deep neural network can avoid the curse of dimensionality. Now for that, we consider the approximation of our function, that means the function f that we are already working with, in terms of the following two-layer neural network. The two-layer neural network is defined here as function of x equals summation of that thing. Now this two-layer neural network includes two sets of parameters. One is ak, the next one is the weights and bias. Now sigma here is the activation function. So the choice of activation function can be anything. That can be ReLU, that can be sigmoid function, or it can be the function of model developer's choice. We consider the supervised learning here, where we know f for a finite data set, and we call this data as the training data that we discussed before. Now this training data D comprises of xi and yi. Here yi is the corresponding label of that xi. Now we already discussed that f, the value of f, is known in this set, so this f of xi is the yi. Now our objective is to find the accurate estimate of the target function f. So that means it is a, once again, it is a classical example of the function approximation. Now for this we need to minimize the training error. Now we define the training error in terms of this one, that is RF is the expectation of something. Now this f star is the approximation. F star is the approximation of f. Now since it is an expectation, we can replace it with the integration. This is the integration. Here lambda is the distribution of x on the domain capital X belongs to RD, d-dimensional space. Now the standard procedure for supervised learning includes three steps. First, choosing the hypothesis space. Here the hypothesis space means the seat of all trial functions. Here we call the hypothesis space as HM, where M is the dimension of the hypothesis space. Now by the dimension of the hypothesis space, we mean that the number of free model parameters available, as we can recall it from our previous slides. Now, classically, we choose the polynomial functions, wavelets, but in this case, we use the neural network since we need to understand how the neural network avoids the curse of dimensionality problem. Now, the second step is to formulate the optimization problem. That means we need to come up with a loss function. So what is loss? Loss is the deviation from the original and to the approximated, right? So we need to calculate this distance, that is the from the original f to the approximated f, and this is an L2, right? So this we call the loss function. And the step 3 is the training. We need to solve the optimization problem either using the gradient descent or using the stochastic gradient descent or using some other choices. It depends on the choice of the model developer. So the total error can be computed as this f minus f star, where f was the original function and f star was the output of the machine learning model. Since it is a function approximation problem, now the classical way to represent a function is the Fourier transform, this. Now if we do the approximation using the discrete Fourier transform, then the result will suffer from the curse of dimensionality. Now instead, if we define a probability density, probability distribution, that pi, and we represent our function, approximated function, like this, uh, then with a little mathematics we can transform this one to this. Now WL are the IID samples from this pi distribution. Then this is the approximated version, and which can be computed as this one. So it is a two-layer neural network once again. Now if we do the approximation error, that means if we calculate the approximation error, that term does not include any dimensionality. That means this is the from dimensionality. That means neural network can be used efficiently in the high dimensional spaces. In the previous slides, we saw that how the artificial neural network avoids the dimensionality problem. That means the error term does not include the dimensionality, that is dimensionality of the space. So the neural network can be used as a good tool for the high dimensional problem. Now let us talk about some other models, that is called the generative adversarial network. So it's a machine learning model, and mostly it's a deep neural network model, and it's a generative model. So we will talk about the generative model later. Now to define the generative adversarial network, we say that GANs are the deep neural networks, or the DNNs, comprised of two different neural networks. One is the generator, another one is the discriminator, and they used to compete each other for generating non-existent samples. Now both generator and discriminator can be deep neural networks. This could be the structure. So this is the generator and this is the discriminator. So it will generate couple of fake samples, and it will be, it will supply that fake samples to the discriminator, and discriminator will say that if the sample are fake uh, or uh, real. Now GANs are trained in an adversarial manner to generate data imitating some unknown distributions. So we will see all these things one by one in the next slides. Let us talk about the discriminative model. So a discriminative model learns a function that maps an input data to a desired class label. That means it tries to discriminate between two different classes. So to do so, they put a lot of effort to model the decision boundary between two classes. And, and in that case, they mostly do not consider the points that are lying far from the decision boundary. Hence, the discriminative model ignores a lot of label data since it only looks at the points that lying very close to the decision boundary. Now, discriminative models are very powerful if you have a lot of data, the training data, and the data must be labeled because discriminative model cannot be used in the unsupervised learning and cannot be used with the unlabeled data. Now we find a lot of well-known classifier that implements a discriminative model. Now directly, if we see that a discriminative model learns the conditional probability distribution, that is y given x, probability of y given x. Here x is the image and y is the corresponding label, right? So the output of the discriminative model must lie between 0 and 1. Now if it is 0, that means x does not belong to y, and if it is 1 means x is a member of y. But if it is 0.5, that means our discriminative model is very confused about the situation of x. We talked about the discriminative model, and we can recall that the job of the discriminative model was to distinguish between two samples from two different distributions or two different classes, right? Now the goal of the generative model is totally different. Our goal here is to generate a lot of samples, and all the samples are all the samples are fake because they are non-existent, they are generated, crafted. So let us define the generative model G. Given the training data, the goal of the generative model is to generate a lot of samples from the training distribution, and it learns the joint probability of the input and the label simultaneously. Now one thing is quite clear, that all the new samples prepared by the generator, they are all fake. So these are the new samples prepared by the generator Z. They are all fake. So initially generator takes an input from the arbitrary random noise. So we call this arbitrary random noise distribution is script Z. So we take a sample from this arbitrary random noise distribution. Now then generator receives that sample and generator prepares an output. So generator prepares a lot of output, and those outputs, these are all fake outputs, and those outputs must have a distribution. We call this distribution as G of script Z. Now by the property of the generative model, we must have to make this G, Z and X as close as possible. Now mathematically, this G means the generative model, maps one sample from that input random noise distribution to the fake generated distribution. This we call the generated distribution. So and then the divergence or the difference between this distribution, that is the fake distribution, and the original distribution or the true distribution, we can measure it using L1, L2 norms or JS or KL divergence. There are several other measures that we will see later. So let us talk about the GAN architecture, not the generator architecture. The architecture used in this slide is pretty common. Now, as we discussed, that GAN consists of two things. One is called the generator, another one is called the discriminator. We call the generator as the G theta and discriminator as the G. Now we can recall from the last slide that generator's job is to generate a lot of information, lot of fake samples or fake data, whatever, and generator's objective is to distinguish these fake samples from the original data. So we take the celeb data as an example in this slide. So now everything starts from the latent space. Here latent space is the random arbitrary random distribution. That arbitrary random distribution, we call it as script Z. Now from that arbitrary random distribution we took a random sample, that is Z. Now this will be the input to the generator G theta. Now once generator receives this input, it processes and will generate a lot of fake samples. Since our example was the celeb data, so we have successfully generated a lot of human faces. Now since they are a lot of they are fake human faces, so we call their distribution is G theta of script Z. Now since the goal of the generative model is to make these two distributions, that means G theta Z and X, as close as possible, then we include another component. We include the next component called the discriminator D. So D judges, since as we recall that the job of the D is to discriminate between the original and the fake sample, so D tries to discriminate it. Now if D says that this is correct, that means this is the original data, so we can call that D is pooled. But if it says no, then we do the back propagation. So that is the fine tuning. So fine tuning means the back propagation. That means back propagation, using the back propagation we fine tune the weights of this discriminator as well as weights of this generator network. So once the weights are adjusted, the generator will produce a lot of information, lot of fake samples once again, and those fake samples will be given to the discriminator. Again the discriminator will continue judging that fake samples with the original, and again it says something correct or not. If it says correct, then everything stops. If it says no, then again the fine-tuning continues. That means again the readjustment of the weights of the discriminator as well as the readjustment of the weights of the generator, and this process will continue until convergence. So just to recall, in the last slide we saw the basic architecture of the generative adversarial network that comprises of two things. One is called the generator and other one is called the discriminator. So the job of the generator is to generate a lot of fake information, this where the discriminator takes all the fake information as well as the real information. That is, last slide we saw the celeb data, so real information, and tries to distinguish between the fake and the real. That was the job of the discriminator that we already discussed. Now in this slide we try to understand what goes internally. That means how an arbitrary sample from this arbitrary noise distribution got transformed into a fake human face. That is the generated distribution. Now in short, or more clearly, we try to compute the density of this fake samples, distribution. That means the generated distribution. So to do so, to let us assume that X be the original data. So here X is the original data. In our last slide we talked about the celeb data, we remember, and Z be the arbitrary input noise from arbitrary input noise to the generator. So this is the Z arbitrary input noise to the generator. Obviously it came from the latent space. So these are the random variables defined on sufficiently regular spaces X and Z respectively, with the respective Borel probability measure X, script X and script Z. So script X for the original and script Z for the fake, not fake actually, for the latent space, for the latent space distribution, we can say that. Now the arbitrary noise Z, this Z to G theta creates fake samples. So these are the fake samples, and then by the change of variable we can determine the probability density function of this. And I mean, we assume this is the density function, probability density function, phi subscript x tilde. So these can be computed using this transformation. So this is a very important transformation that almost every generator does. So in the last slide, we saw that what happens internally when a tiny sample from the input latent space was converted to a somehow meaningful fake human face. And we also saw the transformation applied on the input noise, I mean Z, that we can recall to convert it to a fake human face. That transform, we recall the transformation. Now, in this slide, we try to understand that what needs to be done to make the fake sample look very real. So one thing, we have to minimize the divergence between the original distribution, that is the script X that we already assumed. This is the original distribution, and this is the fake distribution, that means the generated distribution. So what we have to do, we have to compute the discrepancy between these two, and we call the discrepancy as the epsilon. Now, from the generative model's goal point of view, what we have to do, we have to minimize this thing, that epsilon of x and z. So actually this, we need to solve this optimization problem. Discriminator's job is to distinguish between the real and the fake samples, where the real samples can be gathered from the select data or other available data over the internet, whereas the fake samples are created by the generator part of the generative adversarial network that we have already seen in the last slides. Now, more formally, let us define the job of the discriminator. So let x and x tilde be the random variable defined on a sufficiently regular topological space X with respective Borel probability measures, that is script x and g theta of script z. So we already know that the script x is the distribution of the true data, or the true data distribution, and g theta script z is the distribution of the fake samples generated by the generator. Now we took two observations, x and x tilde, where x is the IID from the true distribution and x tilde is the IID from the fake sample distribution. Now, the goal of the discriminator is to identify if the true and fake distributions are same or not. Now, for this, it uses two sample tests with the notion of the discrepancy. Now, these two sample tests has two hypotheses. It's called the one is called the null hypothesis, which says the original distribution is very similar to the fake distribution, whereas the alternate hypothesis rejects the null hypothesis. Now, ideally, if the discrepancy between the original and the fake distribution is zero, which this implies that original distribution is very same as the fake distribution. But this is a quite ideal case. Now, how to achieve or how to obtain this number? So for that, we generally design an estimator that is called the epsilon hat. If the value of the epsilon hat lies, is more than R alpha, that means the rejection threshold, then we will accept the alternate hypothesis and reject the null hypothesis. That means the original distribution is very different from the fake distribution. That means the discriminator successfully identifies a fake sample. But if epsilon hat lies below R alpha, then the null hypothesis will be accepted. That means the original distribution is very similar to the fake distribution. That means the discriminator fails to identify a fake sample, and the goal of the generator is was satisfied. Generator in a generative adversarial network tries to minimize the discrepancy between the original and the fake distribution. Why? Because The goal of the generator is to fool the discriminator. However, the discriminator wants to maximize this discrepancy because it helps the discriminator to uniquely identify a fake sample and real as well. Now, following this logic, we can construct the objective function of a generative adversarial network as a two-player minimax game where one party, called generator, is trying to minimize this discrepancy, whereas the other party, discriminator, tries to maximize the discrepancy. Now, same thing is here. The discriminator D is trying to maximize its reward, this if you call this quantity as reward, whereas the generator G on the other hand tries to minimize D's reward or maximize its loss. Now, training criteria for the discriminator is this, whereas the training criteria for the generator is this. Discriminated training in a generative adversarial network. So as we already know that everything starts with the latent space, which has a distribution of script Z. Then we collected one sample, random sample Z from the latent space, and which will be the input to the generator G theta. Now G theta receives the input and processes a lot and generated a series of fake samples. On the other hand, we also have the series of real instances collected from the celeb data. Now, discriminator generally implements discriminative modeling, which requires a lot of label data, and discriminative model mainly implements supervised learning. So we put y equals 0 as label with the fake instances and y equal 1 as a label with the real instances. Now we supplied all the data to this discriminative model D, and accordingly the discriminative model will produce some outputs, and in this way we train this discriminator in a generative adversarial network. Now it is quite similar to the classification problems and training a CNN having two different output nodes. So when we train the generator, we will keep the discriminator fixed. That is, we will not train its weights and biases. The reason for doing this is we do not want our discriminator to become too strong to beat. We create multiple noise Z from that script Z, and feed these to the generator to get artificial instances, and we want our discriminator to get fooled by these images. That is, produce the output as 1. Now in this case we label the artificial instances as 1 since we are trying to make our generator smart enough so that it can fool the discriminator. If it fails to do so, then the errors are backpropagated and the weights and biases of the generator network will be adjusted so that it becomes more intelligent and will produce outputs that are more close to the original instances. So in this way we train the generator. Now, in the previous slides, we saw how to train the generators and discriminators in the generative adversarial networks. Now, in this slide, we try to understand what happens in the distribution level. So as we already discussed, that input noise, the samples from the input noise are the inputs to the generator. So all the red dots, they are the samples in this distribution, samples of these distributions. Now after receiving these inputs, generator will compute and produce some fake samples. Now these are all the fake samples. These are all the red dots are the fake samples, and the fake sample has a distribution called GZ that we saw in the last slide. Now this is the shape of the GZ after 10 iteration. Now by the property of the generative model and as well as the generative adversarial network, now these two, that is GZ and X, should be as close as possible. Now, the shape of this GZ is pretty different from the shape of the original distribution. Now, these samples, along with the samples from here, will be the input to the discriminator. This is the discriminator D. Now, discriminator will compute the discrepancy, this epsilon. Now, epsilon hat, how to compute the discrepancy? If we can recall that epsilon hat is the estimated for this discrepancy, and if the value of epsilon hat is greater than that R alpha, so then we will reject the null hypothesis. What null hypothesis says? Null hypothesis says that the original distribution and the fake distribution are same. So that means we accept the alternate hypothesis. That means these two are not same after the iteration 10. Now, if they are not same, then we will do the retraining. So retraining means retraining of the discriminator as well as the retraining of the generator. So retraining of discriminator means readjustments of its weights and biases, and similarly the retraining of generator means the readjustments of its weights and biases. Now, after the retraining, then it will prepare a couple of fake samples, and maybe after the iteration 1000, so the shape of the fake distribution, this is the fake sample distribution, is like this. Now, once again, these samples will be given to the discriminator along with the samples from the original distribution. Now, these are the inputs to the original these are the inputs to the discriminator, and discriminator will compute once again the discrepancy. So if this again happens, then once again it will retrain the discriminator as well as the generator. That means readjustments of weights in discriminator and generator, and after these readjustment, once again it will prepare a couple of samples, and maybe after 1000 iteration, this is the shape of the fake sample. Now, these fake samples, and this is the original sample. This is a fake distribution, not sample. This is the original distribution. Now, these two shapes are, somehow not very different. Now, once again, this retraining will continue, and we get this shape after 10,000 iteration, which looks very similar. Maybe after a couple of other iteration, we may, the disk generator may be able to fool the uh, discriminator. That means this epsilon hat will be less than R alpha, where R alpha is the rejection threshold. So in that case, as we can recall that our null hypothesis, that is H naught what is equal GZ, will be accepted. That means discriminator is fooled. The integral probability matrix generally compute this discrepancy, that means between the original and the fake distribution, using generally two discrepancy measures. One of them is called the F divergence, and the other one is the integral probability matrix. We call them IPMs. Now, let us discuss one by one. So F divergence, let x and g theta be the distributions defined on this space. Now, and we also assume that g theta is absolutely continuous with respect to x. Then for a convex function, that f from 0 infinity to r, which is strictly convex at 1, that is f1 equals 0, then f divergence of g theta from x is defined by this quantity. Now, this is the f divergence of g theta from x. Now, if both x and g theta are continuous, then this expectation will be replaced by the integration, and if they are discrete, then this expectation will be replaced by the summation. Now, there are since we can find one ratio here, now f divergence is also called the ratio based divergence. Now, there are a couple of famous F divergences available. So one of them is called the KL, another one is JS, and apart from that, there are several other divergences available in the literature. Now, KL divergence of g theta from x is defined as this quantity, where phi x is the probability density function of this x. Since we assume that x and g both are continuous, that's why we replace this expectation by this integration. Now, this phi x is the probability density function of x, and phi x tilde is the probability density function of g theta z. We saw it in the previous slides. Now, KL divergence is not symmetric. That means KL divergence of this from x is not similar to the KL divergence of x from g theta. Now, the symmetric version of the KL divergence is called the JS divergence. This JS divergence, as we can see that it is the summation of it is the sum of two different KL divergence. So this PM is defined as this one, and JS divergence is symmetric. That means JS divergence of g theta from x is very much similar to the JS divergence of x from g theta. We already talked about the F divergence in the previous slide. We also saw a couple of well-known F divergences, that is called the KL and JS divergences. And apart from that, there are a couple of well-known F divergences available, that are the squared Hillinger distance, total variation distance, and so many more that can be found in the literature. Now, in this slide, we talk about the integral probability matrix, or the IPMs. That is the another alternative to measure the discrepancy between the real and the fake distributions. Now, in case of IPMs, we generally choose the class of functions from x to r, and we try to compute the distance between the real and the fake distributions using this rule. Now, what this rule says, so here we try to optimize our test function. This is the test function, to maximize the distance. Maximize this distance. So what this distance means, so it is the difference between the expectations of the test function f over the real distribution and the expectation of the test function f over the fake sample distribution. So we call this distance as the integral probability matrix. Now, in literature, we can find a lot of GANs who are using these IPMs to measure the discrepancy between real and the fixed sample distributions. Now, for example, if F be the set of classifier, that means our chosen set of function is a set of classifier, then we call them as the basic GANs, and a lot of examples are available, such as GANs, C-GANs, DC GANs. They are very well known. Now, if the set of function is a Lipschitz 1 function, then we call this distance as the Wasserstein 1 distance. We call this distance as the Wasserstein 1 distance, and a lot of GANs available in the literature who use this Wasserstein 1 distance. Now, for example, WGAN, WGAN GP, RDGAN, etc. Now, if this class of function or the set of function is this, or the total variation, then the corresponding GAN we call the EB GANs. If F is the mean error of the autoencoders, then we call this BE GANs. If this F is chosen as a function in an unit ball over the RKHS, then we call this distance as the MMD. We call this distance as MMD then, and a lot of GANs, including MMD nets, they are using this this measure. We saw the integral probability matrix, the definition of the integral probability matrix in the last slides, and we also saw that how different classes of GANs use different classes of integral probability matrix. For example, in case of basic GANs, the measurable set of measurable function f was replaced by the set of classifiers. Now, however, if we see the basic GAN literature, we might find that in case of vanilla GANs, C GANs, DC GANs, and a lot of other basic GANs, they mainly use the F divergence to measure the discrepancy between the real and the fixed distribution. Now, they mainly use the mostly used F divergence measure is JS divergence, that is called the Janssen and Shannon divergence. However, in a very few cases we can find the usage of the KL divergence. Once again, that is also an F divergence. Now, KL divergences are mostly mostly used by variational auto encoders. Now, these JS and KL divergences are relatively unstable. Let us talk about why. Now, the KL divergence, we find that it often shoots to infinity for any two non-overlapping distributions. However, the JS divergence becomes log 2 for any two non-overlapping distributions. Hence, we call them relatively unstable. However, the JS divergence becomes more stable than the KL divergence. Now, for example, let us see that, for example, it is very hard in reality to have an overlap between X and the fixed sample distribution. So in all those cases, JS divergence will produce this log 2. So, and in case of the vanilla GAN, they showed that using JS divergence, the GAN model produces vanishing gradient. So that's a big problem. But however, the GANs using IPMs, they have strong convergence, mostly the Wasserstein GAN, Wasserstein class GANs like WGAN, WGAN GP, they have strong convergence. Even RDGAN has very strong convergence. RDGAN is a conditional structure. However, these two models are not conditional. MMD GANs, they use the MMD as the discrepancy measure. MMD as the discrepancy measure that we saw in the last slide. Now, discriminator implements IPMs like Wasserstein distance, max mean discrepancy, etc. That means the GANs using IPMs. In this case, the discriminator implements these Wasserstein distance, max mean discrepancy, such measures. So let us talk about the problems, other problems of the basic GANs. Basic GANs means the vanilla GANs, C GANs, and all such type of things. If we can remember that basic GANs mostly tries to replace this set of measurable functions with set of classifiers. So since this is set of classifiers, then the generator's job is to minimize the power of the two sample test. That is, it tries to minimize the accuracy of the discriminator. Now, the generator of these basic GANs are mostly trained on the previous discriminator, whereas the discriminators are trained on the samples provided by the previous generator. So, while discussing about the training of generator and discriminator in a generative adversarial network, so this was generator and this is the discriminator. We mentioned that while training the generator, we fix the discriminator. That means there is no training on the discriminator. So this is an already trained discriminator. Now our job is to, the job of the generator is to produce a lot of fixed samples, and these fixed samples will be judged by the discriminator. So if the discriminator says these are not the real samples, so certainly generator will be trained and no training for the discriminator. But if the discriminator says, training for the generator means the weights and bias of the generators will be recalculated, and after the recalculation of the weights and bias, generator will produce another set of fixed samples, and which will be thrown to the discriminator, and the discriminator will judge again that sample is fake or not. So if the discriminator says they are fixed samples, then once again the generator will be trained, and the weights and bias will be recalculated, and again this process will continue. But if the discriminator says that yes, this is the real sample, then generator training will be stopped. Now same thing will be done with while training the discriminator. So we try to train the discriminator on the previous generator. So it is surely a two-stage problem. That means the generator will be trained on the previous discriminator, and the discriminator will be trained on the previous generator. So this is the two-step optimization problems, which requires a lot of synchronization in between. But in most of the basic GANs, they are suffering from the lack of synchronization, which gives rise to the mode collapse related problems and unstable training. However, however, we find that the other IPM based GANs, such as the Wasserstein GANs, such as the MMT GANs, they have excellent convergence and very stable training. So this is the pictorial view of the GAN classification based on the discrepancy measure. Now the GAN can be classified in two parts, can be distributed in two parts. One is GANs using divergence, F divergence, and GANs using IPMs. So all the basic GANs falls in these categories. Of these basic GANs, they may mostly use the function F, that is the set of measurable function as a set of classifiers. Now a couple of supervised models are there, that is GAN, CGAN, etc., and couple of unsupervised model including DC GANs. Now GANs using IPMs include the Wasserstein GAN. So in this case, F would be the Lipschitz 1 function that we can recall. This is the Lipschitz 1 function. In case of the energy based GANs, this is the set of measurable functions. In case of the MMT GANs, the set of measurable functions include these, as we can recall. So this is the open wall from the RKHS, this is the B GAN and the diffusion GAN. Apart from that, there are several other GANs who use the IPMs. And this is the end of my presentation, and thank you for your patience. And if you have any question, kindly ask, please.
Hello everyone. I will talk about today on the cyber kill chain. The cyber kill chain is an adaptation of the military kill chain, which is a step-by-step approach that identifies and stops enemy activity. It was originally developed by Lockheed Martin in 2011. The cyber kill chain actually is similar, but it outlines the various stages of several common cyber attacks and by extension, the points at which the information security team can prevent, detect, or intercept attackers. In the side image, we can see some of those stages. Researchers has been divided those kill chain in the different type of stages, but most common stages are reconnaissance, weaponization, delivery, exploitation, installation, command and control, action on objectives. There's other similar term like weaponization also and delivery, also known as same stage by other researcher. Action on object is also known as the impact. Installation known as the lateral movement, or other name is based on the different research. So cyber kill chain plays an important role in helping organization define their cybersecurity strategy. As part of this model, organization must adopt service and solutions that allow them to detect attackers, which each stage, prevent access, stop sensitive data, response the attacks in the real time, stop lateral movement of attacker within this network. So this kill chain actually helps the organization most. Similarly, adversarial attack can be also described using a kill chain, and the goal for that is the reason that security researchers who are familiar with the cybersecurity kill chain, they will be more familiar with the machine learning based on the attacks on the machine learning. That will be, if we can represent that in a similar kill chain, that will be more familiar to the cybersecurity researcher. So that was the goal, and to achieve that, we divided the kill chain in 7 parts, which are the reconnaissance, exploitation, initial access, execution, evasion, exploitation, impact. And you can see I also gave the similar terms in the similar section. Let's start with the reconnaissance. In this stage is actually the information gathering stage. Other cybersecurity attacker actually target mostly the social media based information, other open source information, company org data, website data, scraping data. That was the goal in this stage for the other cybersecurity attacks. But for the machine learning attack, it will be more narrow. They actually will target the technical publication in the RZ, whatever the paper published on that model, public blogs. The company released white paper where they talked about what model they used, different conference proceedings of the journal papers or software repository or GitHub. So you can see that in reconnaissance stage, the social media posting or tweets is not important. What is most important is the open source information about the model. Next, we can talk about what the attacker's goal in this stage. Attacker goal is this stage to identify what the ML model pipeline is there. By the pipeline, that means what feature engineering they do, what is the weight of the, what if the model is a well-known model, what are the weight in there, what features they use, what algorithm is it, gradient based or non-gradient based, and what are the parameters, weights of the architectural model. So those information need to be gathered. Different model repositories of GitHub, mostly all of are in open source. They can gather those information in there. So from here we can see that if our if anyone developed a machine learning model with less known machine learning algorithm techniques or others, that model will be less vulnerable than very much well-known models. So that's why you can suggest that companies should use more lesser known models or model which has some unknown feature processing or other layers inside that, so adversary can't identify the pipeline easily. Next stage is the weaponization. In this stage, two things was done: exploiting the physical environment, which is done with the first stage. Adversary actually collect the data sets, and data set actually collect using the open source information technology, and based on that, adversary can create the model. It can also get the model by exploiting API. It will create the shadow model. The way shadow model works is that the input of an actual model and that output of the actual model will be used to train a new model that will be known as the shadow model. If attackers have the API access, it can use that to build a shadow model, and from the shadow model, it can guess the decision boundary of the target model or the weights of the target model. That can classify as the weaponization stage. Countermeasure can be that using the less known pre-known pre-trained model, because many researchers use the pre-trained model which was trained into one dataset, use that to another dataset. Those pre-trained models are well known, and also we should use the complex model which are less transparent and less explainable. So shadow model generating is a hard, but that also has some trade-off, because the explainability and the trustworthiness of those models will be also in the question. So it will be a kind of the balancing between those two. Next stage is initial access. And initial access is getting the access of the API, getting the product of service, getting the system where the model is deployed, that access, or getting the access of the ML model. And countermeasure is very same as the cybersecurity. Other cybersecurity attack using the traditional well-equipped network and software defenses such as a good firewall, good virus detection systems are good enough to countermeasure the attacks in these stages. Next, we can talk about the execution. So execution can be happen in if the attacker got a system, he can set a pre-trained ML model with a Trojan backdoor. It could also included the executing unsafe ML models. Also, it can do several execution using inference API like membership inference attack, and also can do the ML model inversion. So execution pre-trained ML model with a backdoor is a kind of a ready-to-use models. It can quickly deploy it, and it can also very easy to set up. So if the attacker got access to the system, it can change the model with its pre-trained ML model with a backdoor, or it can deliver ML model with backdoor to the client from the vendor, and it can be so it's kind of like a software delivery where the software is itself corrupted. And also unsafe ML model is very easy to execute. The attacker can do some PKL embedding or introduce some malicious data payload in the model. And execution and ML models from downloading the compromised sources. If someone wanted to use the publicly available ML model, and if it tried to download from the open source, some of the sources are compromised, and we have a backdoor. And most of the model files are saved with the PKL, which is a very easy to reverse engineering, and that can have some malicious backdoor also. And also the inference API can be used by the attacker in this way. And also the reconstructed ML model can use a different API, which will be very hard to detect. So the countermeasure of this attack stage, we can say that using a highly monitored inference API and try to flag any anomalous activities. So it will be very similar as the intrusion detection, but the more emphasis would be the inference monitoring the inference API, and anomalous activity in the ML input and outputs need to be checked. And the evasion on the lateral movement section, it was attacker tried to use some input modification, so he will not be in the network, but it still can do harm. And also it will try to avoid the intrusion detection system in the what the ML model was deployed. And so the countermeasure of that would be the using a Trojan AI detector system, and also use some safeguard against the adversarial input, which are the evasion-based attacks. If they are deployed in the system, so in this stage, the ML model can be work against them. And exfiltration, it could be the stealing of the model. It is the same as the exploiting an inference API, getting stealing the data of the model and architectures. It will be also damage would be the stored intellectual property, and this can be done in the insecure storage if the training data was in the insecure storage. That can be exploited to discover the ML pipeline and the intellectual properties. And the impact of those attacks can be that this can be create the very much adversarial data inputs which can be physically used. They can support the system just for fun or trolling, or they can also damage some attack. These things they can do by poisoning or evasion or exploiting common vulnerability in the ML development packages such as in Python. And also it can use to create a denial of services, like they can use the inference API to provide lot of wrong information, or they can make the ML model to run more than required, which will waste the energy or computation power in the target system, and that can cause a wide server downtime. So MITI Atlas is actually trying to introduce this in the more detailed way. Here is the reference Atlas MITI.org. Some of our resources was inspired by them, and they have a more detailed information of each of them. If our listeners are interested, they can go to the Atlas MITI.org and they can learn more about this technique. Thank you. So I will now move to the next section, where we will in model accuracy, and also it can can't be employed in the deployed system. It needs to be done in the training phase. And generating the adversarial example also troublesome work, because there is a different types of attacks and new attacks are coming every day, and we can't train the model every time a new attack is come. Another process is input reconstruction or transformation. Changing the input in a squeezing, the method resizing is actually work better, or do multiple image for a class, that also work as a defense. But limitation is it's a vulnerable to the adaptive attack. If the attacker know the what type of defense is used, he can bypass that by working on a query-based method based on that defense. Another is the model modification. Change some of the architecture which will be specified for the adversarial attack, but limitation of it is in that it need to change the architecture on the model in the deployed system, so it's a limited applicability. We can't use that in everywhere. So let's see what are the adversarial attacks as some of the limitation also. We did an extensive study on adversarial attack, how they perform in the physical world. So here we can see that we have a different type of adversarial attack. What we did is we printed those in our paper, and we see that they still act as adversarial or not. It was very interesting to see that most of the adversarial attack, which are very famous, like Carlini Wagner or Deepful, they don't perform when you printed them. And also there's an environmental factor as well, such as we did some of the image resized and back the size again, then those not working rate also get increased. We rotated some image, then also they are not working as adversarial. We create a motion effect by blurring the image, then it was also
kind of completely diminish all of the CW and deep full attack effectivity rate. And we also, there's a illumination which is the increase in the brightness of the image, and printed that out. That also destroyed the adversarial effectivity of those things. Here I was showed that the resize scale and backlash scale. Here the degree of the rotation, and here the blurriness level, and here's the brightness level. The reason behind this is that our physical data, when it is formatted in the digital format, it converted to an integer. It converted to the floating value, and if the noise was added in the floating value, and when it will turn back from the printing, as the color format is the integer, this noise can't come back. It's also similar for the sound and web and other approaches. So the problem is that noise needed to be at a higher level, so that when it converted to a physical format, it still exists. So from our mathematical analysis, we found that for 8-bit single channel color, the minimum noise have to be 0.0019. Here n is the bit color. However, this experiment has a limitation because we saw that if we printed in a different type of printer, as printer actually follow a different color format, so there is some limitation of this experiment. Someone can say that our motion and illumination was not actually real life illumination as we simulated it, but other researcher recently confirmed this experiment, and their result actually aligned with our experiment. And it was seen that based on the whatever the printer is, the destruction rate for deep full CW close to the 100. And I didn't see any of the 1 pixel attacks survive after printed them in a print form. So let's see the problem on the deployed system attacks. Let's see the first is a physical world problem. Physical world is like my face is the input data. It is in the physical world, and I can modify. I can wear a sunglass. I can put a sticker on my face, which can misinterpret the machine learning model. And second is the input sensors, which will take the data. CCCam could be an input sensor. And in the first layer, in the input sensor, there can be some modification could be done. Like there is an attack of adversarial patch where a camera lens, a sticker was put on the camera lens, and it classify image differently. This is one type of can happen. Also, the changing the framework, changing the firmware, or configure something in that sensor system can create the adversarial attack. It is one of the attack point. Second attack point is when the sensor is going taking the data, converting the data to digital format, and then sending it to the model. It is going to a communication channel. In this channel, someone can modify that, and this is the only way that higher low part of base attack can work, because here the data is already converted in the binary and the floating point, so there is no environmental factor like as brightness or rotation. Those are not working in here. And then but however, I think this communication channel security is not up to the ML ops. And the second layer is on the operating system is in the place. And now you can say that here can the attacker can change the data before sending it to the ML model. But what we can argue that if the attacker can change the data in here, he doesn't need to add the noise here. He can change the full input because it is not visible by the human or anyone. And he actually effectively actually controlling the full system in this place. He can control the output as well. And the fifth, when the change architecture ML model is changed, it is the kind of the tricky one because we need to verify the outputs are consistent with the other outputs came before. This could be the one of the way it could be a tricky things. And the last on the output medium is like printer or some kind of control who is taking the decision based on the ML output. There could be some kind of attack, but I also think this will goes outside our purview. In this presentation, I will mostly focus on the attacks which happen in the physical world and which can consistence of the ML model. So these are proposed solution. We will check the input, and we will add a input filter which will diffuse the evasion-based most of the attack. And when the output will come, we will check a output filter, will check the consistency of those output as the before output to find out there is any Trojan AI was involved or not. Here I am showing the different adversarial attack types of the evasion-based attack. This is a very generalized form. It is not actually represents, but it is a good to that there is a differentiate between those attack types. Like in the FGSM attack, in the upper I just simulated it, and lower is the actual FGSM. In all of the FGSM image, we can see the scattered noise, which is a different color level. In JSMA, there will be a added perturbation around the actual object. In CW, there is some missing bit or some added bit, which is very hard to distinguish. And diffull is more advanced. Only 1 or 2 pixel has been changed to change that change the output. This actually gives us an overview that different attack works in a different way. So what we did was, if we apply the filters, it will change the image, and if we differentiate it, we can find out those changes. So like if we run a smoothing algorithm which can remove the noise, we get a new image. If we subtract this image from the previous image, we'll only get the noise, and the noise between the clean image and the process image will have a significant differences if we check the histogram averages. And this difference can be used to classify them. One is adversarial and one is not adversarial. So what in our model actually does, we take the clean image set, we run some of the filters, check the differences image, and take the image properties like as mean value of the histogram and signal to noise ratio. And for the adversarial image set, we also take those value, and we create a rule-based method that if the histogram mean and SNL value is in that level, they will be classified as an adversarial image. If not, they will classify as a clean image. So here is one of the sample. It's converted to histogram. Adversarial image is converted in this way, and clean image has a less noise. If we did a color map, it is more evident, and we can do take the signal to noise ratio by Fourier transform, and we can see that there is a difference of the adversarial image and the clean image. So we did on at least 100 of the filters, and we take all of their histogram value, and based on that difference, we try to classify them. We can see that CW2 has actually no effect of this, but we also showed that CW has a diminishing rate when it comes to physical example, and we will actually work on the physical example, but it is actually work very well against the other attack types. So this is one of the example we showed. Here we done the adaptive smoothing, and here we take the differential image. We can see that clean image differential image has very distinguishing between the other types, and diffull CW actually can't be differentiate much, but it is see that FGSM and JSM can easily treat by adaptive smoothing. By adding additive noise, it is very easy to detect CW2, but not JSMA attack. So different filter actually works better for different attack type. So we test with the gradient-based attack and decision-based attack, and we use 6 type of filter. I classify them by using 6 type, which is noise reduction, sharpening, thickening, shrinking, noise addition like blurriness, additive noise, dithering, transform to transform the Fourier, Laplace or Laplace, and texture-based Gavot, sensors, edge detection, Sobel, Kenny, analytical distance, and more. If we can see that here the same noise addition and noise cancelling filter work for those 4 type of attacks, which are actually from the same attack family, and those are not work well with the diffull and hop skip jump, but the texture based filters actually work with the good with the decision based attacks family, but it's not as well as with the gradient attack. Also, if we take the best performing filter for one attack type and apply it to the other attack type, we can see the best attack type in the FGSM quite well work with the other attack type, but not with the defined family. And it is actually goes same in the other way also. So based on that, we can see that we need a multiple class family, and that will be work better. So in our experimental setup, we took different types of attack and do the more differential based on their category they formed. And we use dataset mainly MST, CFR, ImageNet, and the attacks was formed using ResNet and a VGG model, and also some of use the CNN. And we used only two metrics, signal to noise ratio and histogram average. Initially, we used some other metrics like local binary pattern and other different filter metrics, but we later see that those actually very much correlated with SNR and histogram average, so it was not required. So if we can see that like Gaussian smoothing, additive noise works better for MPGT based attack, sharpening blur works for ImageNet FGSM attack, and different type of combination works for different types of attack. But if we wanted to find those which sequence was best for which type of attack, the total search space is actually immense. For only 50 filter, it will have a huge search, and it will be very tough to do that doing a random or a brute force search. So that's why genetic algorithm comes in the play. We use a genetic algorithm method, and if we say that randomly search, it will take sometime we get 80% accuracy, somewhere before between 80% accuracy, but running genetic algorithm after 20 iteration, we got a close to 90%, more than 90% accuracy filter. This experiment was done for only 6 filters. And if we do the brute force attack where the 8 filter and we try to suppose search the 5 best filter which has an accuracy over 85%, we can see the genetic algorithm search less than others. It is only search a few, and it can get at least 10 number of 10 sequence which has a performance better than 85%, where a brute force search is so huge that we can't able to experiment it for when the filter size is 17. And random search also getting higher as we increasing the filter size. So that's actually gives the idea that using genetic search is a better for this problem. So what we does it, we use a genetic algorithm, and it was working, it was focusing on accuracy and time it take and the diversity of the family. Because as we see it earlier, that if there is a diverse family, it will be work from diverse filter family, it will be work for different type of attacks. So our phenotypes are actually filter sequence, filter 2, filter 6, filter 7, and we calculated each individual accuracy based on their detection rate, based on their time consumption, the time income, and how many filter family was represented in the sequence. It was counted as the diversity level. Based on that, we actually use a multi-objective fitness. We used a utility strategy, and our was terminated when we get a best fitness which was not changed after a certain time. So in the it will work as a way that input data will become, and a set of filter sequence will be selected, and based on that we'll detect that it is adversarial or not. So this is actually the overview of how algorithms work. Filters are going here. GA population was generated by random, and we are checking based on the accuracy, diversity, and time cost. Fitness is calculating, and if the sequence list was not effective with the threshold, we are doing crossover mutation, and I initiated drop operation to maintain the diversity. I will explain that later, and then the new population was actually generated. Okay, so this is the one explain. We did a variable length. This is the phenotype, and we can see that if we change the order, time actually change good. So even for the same order, accuracy will be same, but time consumption rate will be changed. So time is the needed. Here are the filter family sequence. This 3 means these 4 was come from 3 different filter family. One means these 2 comes from 1 filter family. More the diverse is this, it has a more chance to go work against the unforeseen attacks. And the diverseness we have to tackle, there is a 2 type of diverseness. One is the insider diverseness, which is that if these filters are all from same family or not from same family. And as we are giving a dynamic option to select one of the sequence from a set of the sequence, so that set need to be also diverse. So we can't put say a similar sequences. So that is the set diversity. So we have to work with the 2 different type of diversity, and that's why I initiated a drop of operation. When the genetic algorithm first started to work and reached a certain accuracy, I pull off the best performing filters as a pool and remove the most common filters from the population. Then it drop the accuracy for a certain time, but it is again started to climb. And when it reach a certain point, I again do the same operation. I take the best performing sequences and most common filters from there. So the F5 and F11 was not present in this sequence, and here F4 and F1 was not selected in this sequence. So there is a 3 different pool was collected, and every time we give one from each of the pool for the input filter detection. So this is actually genetic algorithm performance rate. We can see the accuracy got rising. The time was fast. The different time was fast is fluctuated, but little time started to reduce. And here we show the average accuracy and the best accuracy, as we need a multiple sequence. So average accuracy was also needed to see. Best accuracy climbed very fast, but average accuracy of the full population set needed time to take climb up. So experimental result will give that this sequence is the filter number 8, 14, 19 has a good F1 score, and diversity was also good, but some of them was the diversity was not good, and we will pick based on this. And this is the Pareto font presentation. I presented as a black are the diversity levels. Accuracy was presented in blue, and filter family diversity was in time was in this side. These greens are actually the Pareto optimal set of my genetic algorithm, and I actually targeting this to use in my sequence. But limitation of this input filter is that I need to generate adversarial inputs for getting taking these filters, and I need to access the clean training data so I can find out that what are the threshold of the noise value. And this method is not actually effective against the Trojan AI and backdoors. And we can say it's dynamic, but it's not adaptive, because filters number of finite. An adaptive attacker can run thousands of query and he can find out what are the defense strategy and he have to overcome. And this system is not actually automated, so it is not good applicable for a deployed ML system. So to remove those limitations, we worked on the output filtering script, and we think we need an adaptive defense strategy which don't modify the learning model and don't require the adversarial knowledge. To do this, we converted this full problem as an outlier detection problem, where we only work on the clean data. We will assume that we don't know any knowledge about how adversarial inputs works. We will only have the knowledge of the clean inputs. So here I represented a MNC dataset using TSNE to visualize how they are placed in the 2D representation space. So you can see that all of the digit has a place and it is clustered when they are clean. When I added 40,000 adversarial sample from 3 different attack set, we can see that this cluster was very much unrecognizable and kind of unseparable of those clusters, and there are a lot of overlap. But this will remove if I use only my SNR and histogram based value to cluster. Here you can see that blues are actually the clean data. This is FGSM attack. This is GSMA, sorry, this is CW, and this is a GSMA attack. So it is very visible that if I work with the histogram and SNR value, applying 14 best performing filters, I did my empirical study, they are actually very separable. And if I only take the clean and adversarial, mean combining all three attack similar, this is also very good separation. So for outlier data, so we are assuming that we only have the knowledge of this clean data. We don't have any knowledge of those. So we did a one-class classification technique, and we pick negative selection algorithm. Negative selection algorithm, to simplest term, suppose you are classify a classification technique where you will classify the dog, but to classify the dog, you will check your input data except everything which are not dog, and if it match with anything else, it is not a dog. It works in that way, and it will generate the data which are not dog, and you will only match with that. It was the simplest way to put the negative selection algorithm. And there is a variation of negative selection algorithm, which is V-detector negative selection algorithm. My supervisor invented this algorithm few years back, and we are working it, and it's very interesting, and it's faster than negative selection algorithm and a process because it using the variable size detector, which was previously mostly used the constant size detector, and there was an algorithm was given. It is just said that it generates the negative samples in a defined variable size, and as negative selection is a random nonlinear, and the variable size also made it unpredictable for an attacker also. And this negative selection algorithm was very good to use in the password authentication system also, which was another interesting one. So what I did is that I take every class level like dog, cat, car, and for each class level, I generated a feature mapping where I take where I generated the negative detector set for them. And so I for more the classes, I have a more I have defined negative detectors for different classes. And in the runtime, it is working as like that input data is coming from the ML model. I'm getting the output level, and as I have the output level and the input data, I'm checking they are fall in the negative detector for the negative detector. If level is 1, I'm checking with the negative detectors for level 1. Is it an outlier or not outlier? If it is a outlier, I am saying stopping it as it's a there is a possible Trojan AI or it's a misclassification, and if it's not, it's going to the output. So why this is working, it will understand in this flow diagram. So input is coming to the ML model, and initially NSA detector is not working. It is going directly to the output, and NSA detector is get trained from the clean data set. So ML model output and going to the clean data set, and with the input and clean data set is generating the NSA detector is initially. And when the NSA detector was generated, it started to check that the new inputs are getting by detector or not. And every time a new inputs are detected as a clean, it was again changing the NSA detector. So there is a consistency with the ML model and the NSA detector. So we can say there is a cold start problem, as initially NSA detector has not enough data, but we can say that if we put clean data first as a test program, NSA detector will get to know this, and this will then NSA detector can automatically update itself as the user are using the ML model. So for example, experimental result, here we show the different attack types and the accuracy of the MST class of 0, 1, 2, 3, and CFR airplane and CFR dog. I didn't able to do the CFR, CW, and default because they actually don't exist in the physical example from my experience. And here's the confusion matrix for all of the digit. And here all three types of attack, FGSM, GSM, and default was used. And we can see that we have accuracy of 95, 96% of the accuracy. If we remove the CW attack, the accuracy will be actually close to 100%. So other than negative selection algorithm, we explore different one-class classification technique as well. There are different classification like linear model, one-class support vector machine, proximity-based HB, also histogram-based outlier score, subspace outlier detection, probabilistic method, COPD, fast COPD, they are also good. Outlier ensemble method are most popular, like isolation forest or feature bagging, and neural network based outlier detection model which works for one class classifications are autoencoder, variable autoencoder, and also a gen based model that are also worked. I also explored those model, and these are the result between V detector and those model. We can see some of those method works actually better than V detector. Like LSCP, it has a very good performance, but it fluctuates some, but which V detector is more consistent. I was surprised to see that autoencoder based and GAN based method didn't work well. I think it could be the configuration problem that we run. We had the low iteration rate, or it is the data set needed to be more, other problem could be happen. But I think the work, the V detector is sufficient, and but still we suggested that we could use the KNN a feature bagging LSCP V detector together and dynamically pick one of them as a model. So this is the basic workflow of our dual filtering scheme, where the ML model will get the input data and it will train the outlier, and the more the input data will come, it is started to train it more. And we get an adaptive attack detection module, which will detect that inputs are coming as very similar or not, because that is a sign of the query-based adaptive attack. However, a patient adaptive attacker can avoid this module, but that will be computationally very expensive. And also the adversarial attack are transferable, so it is kind of hard to control the adaptive attacker in this way. But what we can say that we made the adaptive attacker works harder than before. And the traditional attacks like backpass differential approximation based adaptive attack will not work in here because our negative detector is changing every time. But if someone devices adaptive attack based on our target, that could work, but will be computationally very expensive. So this is the detailed components of my dual filtering scheme. For the inputted scheme, it is a more design which we actually practically implemented. And we can see that here the negative detector was trained. Here the genetic algorithm was trained in the normal data set, was actually updating every time. Adversarial data set also updating in the real time, and new filters was generating, and detector was also changed. So the system was very dynamic and adaptive as it learned in the runtime. And we see that it is more effective than the current defense systems, which has a limited applicability. So in comparison with our other framework, our framework actually works quite well than other methods. And more than that, we have some advantage as our method can start without adversarial attack set. Our outlier detector will detect the adversarial attack, and then based on that, it will revise the filters. So we have that in common. None of those attacks are actually effective against the Trojan AI. Our methods are actually effective, and we don't need to change any architecture of the ML model. We are completely considering the ML model as a black box model. And we don't need the adversarial training, so no reduction of the ML model accuracy also. And our model is not an ensemble method, which is computationally expensive. So that's also a good point for our model. And the summary of full work is that we use a multi-object genetic algorithm, which has a variable length to search the set of filters that will be effective against different type of AS. We devise an adaptive negative filtering methodology to detect adversarial attack that does not modify the ML model or information about the ML model. Our strategy can be implemented in any ML-based system without expensive retraining. We said any ML-based system as because we are completely considering our research on the input, not on the anything from inside the ML model. So it will be same for all ML system. And current adaptive attacks which are proposed last few years, these are ineffective. as we are changing our negative filter detector set, and we are also checking the query-based attack. And further source will be need to conduct more experiment, as my total experiment was more of a on the computer vision domain. I did some of the testing with the sound